Thank you, Nick. It's good to be here, and we're going to take a different tack. We're going to take the tack to us poor folks that don't have 3/10 of an inch per day irrigation capacity, that might have 1/10 of an inch of irrigation capacity, or 1/1500ths, or 2/10. And we know in those situations, for most of our crops, we cannot keep up and keep that water in that root zone to that green area, that we're going to be treading down into the red area. So what we want to think about is how we respond and how do we plan for that situation where we know we're not going to be able to supply that full water. So just put in our heads that we've got that 200 or 300 gallons system over a full circle, and we're trying to make the best economic return we can. Now today I'm going to introduce two management tools, but I've had a lot of help on these, and it takes a range of disciplines or expertise to put all these things together. And you can see up there the soil scientist, economist, data processing, developing the computer programs. I also might mention that we're going to add Nick Kenny to that list because we're trying to adapt these tools that you will see to the Texas situations down here and try to apply for the similar techniques. Now, the two basic questions we're going to be examining today with these two different tools is, first of all, let's look at our longer range planning. When we know we have a limited amount of water, either because of the capacity situation or in parts of our Kansas, they're looking at regulations where they're going to only allow so much water applied every year, or in Nebraska, the southwest corner of Nebraska, they've already gone into these regulatory measures, because if we're going to keep the water or keep some of the water in the aquifer, how's the only way to keep it there? Don't pump it. So we have to be looking at management that will keep us still profitable in those situations. And we're trying to say, well, what crops would meet that scenario of having that much water to work with? How can we put the mixes of crops together? We've already heard about corn on one side, cotton on the other. How do we make those decisions on the different cropping strategies we might have in the long term? Then we want to look, after we've chosen those crops and we're looking at this particular year, how are we going to manage our system to put on the best water for that economic profit? How can we spread that water out or concentrate that water of the growing season? So I'm flipping over the irrigation scheduling that we've heard up until this point to scheduling from the mode of thinking about predicting that irrigation schedule rather than responding to the environment that I have this day or the next 3 days. And we know we can't respond to that environment because we don't have that capacity, we have something limited. So let's go to basics. You've seen the curves, the diminishing recurrent term curve. As we add water, we get less response. But let's look at the real life out there, and these data are from 5 years at Garden City. And what we call relative yield, that means the yield we got on our treatment, there's 6 treatments, the treatment we put on the most water. And we take the yield from the other treatments and divide it by that full water. And we see we come up with a relative yield and put all the years on the same scale. And we go from the high irrigation application down to the low application, and you see a spread in that year-to-year variation in your yield because of the number of years there. And we have to think about that spread as far as our risk management. Because as we pull back the water, we're going to have more variability. You know you'll have that in your dryland management systems, but we're going to have that continuum carrying into the lower application rates. So risk is out there, and some of our tools that we use, we also have to put on our thinking caps and think about what we're going to face as far as risk. We're using models, computerized models, a crop model, to develop all of these, going through the programs and actually the engine of these programs, but I've also compared the model results with the results you saw on the last slide, or again, it's relative yield, and we do have some good correspondence. The upper line is for the experimental environment, the lower line is for the model. They separate at the bottom, and we think that that's probably due to the fact that we had really good no-till management in the plots, where the model has been calibrated for bare soil conditions. And we're working on getting a version which will more match that and go into no-till conditions. We've done some adjustments on part of that model. But still, look at the spread and the risk you're going through as you decrease your water. So the first decision tool we're going to talk about is what we call the crop water allocator. We're allocating that water to different crops and choosing different crops to respond to the water I do have. The crops are listed on the left that we consider. Fallow is treated as a crop because you might retire part of that field. You still have to take care of the weeds, but you retire that part of the field. In particular situations, that's an option. Then we have predetermined splits on how we're going to either split up our farm, split up the field, or in a region, you can have a regional analysis, what would probably be the pattern of cropping. This is not size or land dependent, but we're just going to say a portion of this crop is devoted to one crop, or field to one crop, and a portion to the other crop, or maybe more. So we can have the splits one-way, two-way, three-way, four-way, and a couple other variations. Now, when we examine this, we can take any or all or any number of those crops and examine them, even though we have only 2 or 3 slots to put them in. We might be examining 4 crops. But what it does is take every combination of crop and every amount of irrigation split out of that total, and takes every situation and just calculates net return for everything. Then it stacks up the results, so you have the highest net return, that situation presented to the next one on down. And this is well, got ahead of myself just a little bit. So we're after the net return for all those different combinations. Now that we've gone with our models and come up with the average situation of the same types of curves you just saw, so that we, over 30-year average conditions, and we try to come up with these curves to predict the yield results on the amount of water we put on and over different amounts of precipitation. Each line represents a different amount of precipitation. So you can see the same spread as we decrease the irrigation. It's not the messy data, it's the long-term average. Now to evaluate that risk, what I would do is go in and look at the high precip and the low precip to kind of bracket where you might be in that range of precipitation variability. So how the model works, it'll go into the inches of water you pump or have available. This is net irrigation. Go up the chart to the proper precipitation line and go across to the left to pick up your relative yield. So it's relative yield times the maximum yield. What's maximum yield? That's the maximum expected yield you can reasonably expect from that field. So we can adjust these results based on you have a good producing field or a poor producing field, and that'll influence that yield calculation. That times price minus operating costs is net return. So we are looking at a net return without fixed cost.